Hey guys, welcome back to my channel, and in this video we will be talking about your preparation of haloalkanes. Now when it comes to your preparation of haloalkanes, this is where our journey begins. This is the place where our official journey of this chapter begins. This is where we will be talking about a number of things, a number of methods to prepare your haloalkanes. And in this particular video is focused on your preparation of haloalkanes from your alkanes. We will be focusing on the preparation using alkanes alone in this particular video. Okay, so what is the way to prepare your haloalkanes using your alkanes? Okay, the main method you can say for the preparation of haloalkanes is by halogenation of alkanes. Halo means halogen atom, and halogenation means we are going to halogenate our alkanes. So what is happening? This is your main reaction present here, and looking at this reaction you can see your alkane present here. This is your alkane methane, and it is reacting with this chlorine atom and it is forming CH3Cl. Let me show you this reaction more broadly, what is happening here. Let's write that methane like this. We can write that methane like this. This is your CH3 and an H, and we can write that chlorine like this as well. Now this reaction, the particular thing about your halogenation of alkanes always occur in the presence of sunlight. This is an important point right here. Halogenation of alkanes always occur in the presence of sunlight. And how do you represent this sunlight? You represent it in this manner, H nu. This is how you represent your sunlight. So if this reaction occurs in the presence of sunlight, your hydrochloric acid, your HCl, this will form a bond. Now what is happening is that this CH3 and hydrogen will break, and this chlorine bonds will break, and the new bond will be formed between this hydrogen and chlorine. So your hydrogen chloride will be removed from this particular structure or your reaction, and then your new bond will be formed between your CH3 and Cl. So finally you will get your CH3Cl, and this is your required product. Now this is not, the reaction does not end here. The fact that the reaction does not end here because there will always be a chlorine atom present here, and chlorine will again react with this, and it will keep reacting in a fast manner until and unless your hydrogen atom removes. So your next product will be your CH2Cl2, and then it will be your CHCl3, and then finally it will be your CCl4. So it is a very fast reaction and will keep on occurring so long as your hydrogen atoms are present in your structure. That is, your chlorine atom or your halogen atom will keep substituting the hydrogen atoms present in your structure. So it is a very fast reaction, as you can say, and a mixture of products will be formed in this reaction. Okay, so let's look at some other things in this as well. Let's look at some trends. Now reactivity of halogens for same alkanes, as you can say. What is the reactivity of your halogen atoms for your similar alkanes? Now what is the rate, as you can say, or you can say the reactivity? So the fastest reaction or the strongest reaction will be, or the most reactive is your fluorine, then it will be your chlorine, and then it will be your bromine, and then it will be your iodine. Iodine is the slowest of all the reaction with any alkane, and if you have iodine in it, then the reaction will proceed very slowly, and if you have fluorine in it, the reaction will be very fast. It will be very fast reaction, and it could also be explosive at times. So careful with your fluorine atom here. And if you talk about the rate of reaction with respect to your alkanes, so your tertiary, or you can say your tertiary alkane will be your highest, will be having your highest rate of reaction. This is your tertiary alkane. I'll show you what it looks like. So if you have a carbon atom attached to 3 carbon atoms, then it will be your tertiary alkane. And if you have a carbon atom attached to your if you have your carbon atom attached to your 2 carbon atoms, let's say this, then it will be your secondary alkane. And if you have your carbon atom attached to only 1 carbon atom, then it will be your primary alkane. And if you have your carbon atom attached to no other carbon atom, only your hydrogen atoms, which is your methane, then it will be your 0th alkane. Okay, that is your rate of reaction. So your tertiary alkane will have the highest rate of reaction, and your secondary alkane will have a little bit lower than your tertiary alkane, and then the order is in this manner. Having said that, let's move on to our first product, that is our first process, that is your fluorination. What is fluorination? Whenever you substitute an alkane by a fluorine atom, that is called your fluorination. It is very simple. This concept is simple. Let's say I am considering methane, and I am going to react it with your fluorine atom here in the presence of sunlight. Remember, sunlight is a necessity, or it is an important precursor when it comes to these reactions. So I am going to react it with sunlight, and the product, as you would have already guessed, will be your CH3F. This is your product. This is your alkyl fluoride. Now, and your hydrogen fluoride will be removed from this reaction. This is your reaction occurring. Now, this is a very strong reaction. You can say this is a very highly exothermic reaction. Why is this highly exothermic? Because fluorine, as I have already shown you before, this fluorine atom present here is very reactive. Since it is very reactive, it is extremely reactive, and it is going in a reaction which is very fast, it is highly exothermic. So a lot of heat energy is evolved in this reaction. It is highly exothermic, and since fluorine is very reactive, this reaction can also occur in dark also, so it does not need sunlight. Fluorine is so reactive that it does not need sunlight to break bonds. It can break them by itself, and it can form the new product. So this reaction can occur in your dark as well. This is an exception, and it could also form a question in your midterms or your UTs. Now, since this reaction, if you can look at this reaction, it is a chain reaction. This heat energy is evolved will again influence this reaction, and again you will have your CH2F2, and again this reaction will continue so long you will get your CF4. Now this is a chain reaction, means the reaction will keep on continuing, and your heat energy will keep on evolving. So your heat energy is evolving, your reaction is continuing, so it will be explosive in nature. Exactly, this is explosive. This reaction is highly exothermic, and it is explosive in nature. That is why this method is usually avoided in labs, because it is so explosive, it is so exothermic, it is uncontrollable. You can never control this reaction properly. That is why it is usually avoided in your laboratories. But another method to if you really want to get your alkyl fluoride, you can easily do it by mixing your noble gas. So mix your noble gas with your fluorine, and you will get this reaction rate will slow down, and you will get your major product as your alkyl fluoride. Remember that. So I want you to take a note of this. It is really important here. Okay, so that is about your fluorination. Moving on, when you talk about your reactions and your chlorination and your chlorination and other stuff of this sort, you have to know the mechanism of this. Mechanism is really important when it comes to your understanding how do these reactions actually occur, what is happening, what exactly is happening. That will tell that the mechanism, to understand that, your mechanism is important. So before we understand the mechanism, let's look at another process, chlorination. I'll come back to the mechanism shortly, but let's just look at chlorination as well, so that I can explain the mechanism using chlorination. So chlorination, it is as simple as fluorination, but this process is fairly easier, and it is not as fast as fluorination, so you can easily form the products here. So substitution by your chlorine atom is your chlorination. If you consider an alkane, for example, your C2H6, this is your ethane, and you are going to add your chlorine atom to it. And in the presence of sunlight, again I'm telling you, the sunlight, it's going to play a major role in your chlorination or in your any nation of your halogen atom. So this is going to play sunlight. Now this reaction, what is peculiar about this reaction is that it can occur in two ways. It could occur in the presence of sunlight, as well as it could occur in the presence of heat. This triangle represents heat, okay, this is delta, and it represents heat. So it could occur in two ways, or it could occur in both these ways. And if it is occurring in the presence of your sunlight, then we can say that it is your photochlorination. Like anything that occurs in the presence of sunlight, we always say it is like photo. We always use the word photo if we are talking about light, and this is your photochlorination because it is occurring in the presence of light. And if your chlorination is occurring in the presence of heat, then you will say that that is your thermal chlorination. Thermal is the word which you have heard since childhood, since your 5th grade. Thermal always represents heat. So this is easy, this is an easy concept. If your chlorination is occurring in the presence of sunlight, then you will say that it is your photochlorination, and if it is occurring in the presence of heat, then you will say that that particular reaction is your thermal chlorination. Now the problem with this is there are a number of products that could be formed. Yes, exactly, there are a number of products, or there is a mixture of product that will be formed. So when this reaction occurs, I'll show it here. So when this reaction is occurring, you will get your C2H5Cl, and again this reaction, and again a chlorine atom will come in your mixture, in your solution. Let's say this reaction was occurring in this beaker, and you have got a number of C2H6 molecules present here. Like you have got so many C2H6 molecules present here, and you've got so many Cl2 molecules present here. So this reaction is going to form a mixture itself. So C2H5Cl, another chlorine atom will attack this, and another product will be forming. So it will be your C2H4Cl, and your hydrogen atom will keep decreasing as we go, and your fluorine atom will keep substituting it again and again and again until we reach a stage where your hydrogen atoms are not present in your compound, and you are only left with your carbon atoms and your chlorine atoms. This will be your C2Cl6. That is what you will be left with. So this is a, there will be a number of isomers also that will be forming. So a mixture will be formed, and major and minor products will also be formed here. Now let me show you about the isomers that I am talking about. What are the isomers that I'm talking about? So if we have, let's say if I consider this, if I have this chloropropane, CH3CH2, or if I have propane, and I am going to chlorinate it, or I'm going to do the process of chlorination on this. So I'm going to use my sunlight and I'm going to use my chlorine molecule here, and I am going to chlorinate this. So the possibility is that this chlorine molecule present here can actually substitute this hydrogen atom present here. So it would go here and attach to this hydrogen atom, or it could also substitute this hydrogen atoms. So I'm not going to tell this because it's the same. I'm not going to tell you about this one because it's same as this. If it is attaching here and if it is attaching here, it's the same thing. But this is different here. You can see that it could also go and attach to this, or it could also go and attach to this. So this is a problem here, and this is the concept of isomerism. Here your products that will be forming will look something like this. It will either be that your chlorine atom goes and attach to this particular carbon atom, so it will be your CH3CH and your Cl CH3, or it could also be that your chlorine atom goes and attaches to your CH3. So your structure will look something like this: CH2 and CH2Cl. So here are your two structures. Now what is peculiar about them? These both are isomers of each other. That is, they are having the same formula, that is C3 and your C3H7 and Cl. This is the common formula for both of these, but they are isomers because these are functional isomers, because the functional group chlorine is attached to different positions. So as you can see here, this is your 2-chloropropane, and this one is your 1-chloropropane. So this is a problem here. You do not have a major or a minor. How do you know about the major and the minor product that will be forming? So remember about this thing that I am going to tell you. The tertiary radical here, the tertiary carbon atom, this is your tertiary carbon atom, and sorry, this is your secondary carbon atom, and this is your primary carbon atom. Whenever you have secondary and primary carbon atom, always the chlorine atom, if it is going to attach to your tertiary or if to your secondary carbon atom, that structure will be more stable. I'll give you the stability order. So this is your secondary radical here, secondary carbon radical here. So if it is going to attach to this free radical here, and this is your secondary free radical, so that will be more stable as compared to this one, which is your primary carbon free radical, which is your primary free radical. So this will be more stable, and hence this will be your major product. You do not have to get confused about this part yet. You will get more insight on this when I am going to discuss the mechanism. So I'll talk about this once more after I discuss about the mechanism. Okay, coming back to the mechanism. What is the mechanism? What is happening? What is the what is behind the scenes of this all drama that is occurring here? Dramatic chemical reaction of haloalkanes and haloarenes. Oh my god, what is happening? Okay, let's break it down. Let's get a simple reaction for ourselves. Let's say I am going to take CH4, this is your methane, and I am going to react it with your chlorine in the presence of sunlight, and I am going to get your CH3Cl. This is what I'm going to get. Now what is happening? What is behind the scenes? What is the reaction, and what are the steps of this mechanism that we are about to start? Okay, we do not have to worry. Let's just take a deep breath and just start our mechanism. it is completely easy. You do not have to worry about anything in this mechanism, and it is a fair, recap of all that you have studied before, and I'll try to make it as easy as possible for you guys as I can. Okay, so our first step in this mechanism is our initiation. So we are going to initiate, or we are going to start our mechanism. How do we start our mechanism? Okay, we take our chlorine molecule. So we have got this a chlorine molecule here, and I'm going to represent this chlorine molecule with this bond, and I take this chlorine molecule and I throw some light on this, and I throw some sunlight on this. So I've got my sun here, and I'm going to throw some light on it, and what this sunlight does is that it breaks the chlorine bond, and so your chlorine atom takes away its electron back, and your another chlorine atom takes away its electron back. So what is happening in the presence of sunlight? Your chlorine radicals are forming. So your two chlorine radicals will be formed. So you have generated your free radicals. Your free radicals in your first step. Your chlorine free radicals in your first step. Now what is our second step? Now your chlorine free radicals have been generated, you're all set up, you have started your reaction, and so we will proceed to our next step, which is your propagation. Now after initiation, you are going to need to propagate your reaction. So how do you do that? How do you propagate this reaction? Okay, now this chlorine free radical is electron thirsty. It is needing an electron very badly, so that it could complete the octet rule and become stable. So it is highly unstable and it is electron thirsty. So what it will do, it is going to attack. Like if a lion is hungry, it goes and attacks some animals and other animals and eats up, and it is very unstable at that time. Similarly, this chlorine is just like a lion. It's so electron thirsty that it will go to a nearby methane molecule. This is your methane molecule, and what it will do, it will actually attack this methane molecule. And by attack I mean it will break the bond of this methane molecule. The way hydrogen atom was attached to this methane molecule, it will break this bond, so there will be cleavage in this, and your hydrogen atom is also unstable. Now your hydrogen atom will form a free radical, and this is unstable and this is unstable. So what will happen is that they both will react with each other, and they will form HCl, and they will be getting out of our reaction. And what will we get? This CH3. This CH3, since we did cleavage in this and we broke the bond, so this will form a free radical here, which will be your CH3 free radical here. That is the formation of your methyl free radical, and your HCl is out from the reaction. So we don't need to worry about that. And now what we are going to do is, now this CH3, what it will do is, let me write it here. Now this CH3 free radical, it will go and attack. Now this is also electron thirsty again. Free radicals are always electron thirsty. They need somebody to complete their octet. They need to share some electrons so that their octet is complete, and they are going to become stable after that. So again, this CH3 or your methyl molecule is unstable, is just like that hungry lion. So now it will go and search for your chlorine atoms, chlorine molecules. So it will go and attack your chlorine molecule, and again, since it will attack this chlorine molecule, the bonds break, your chlorine molecules go take away their electrons, and a chlorine free radicals are formed, and this your methyl molecule or your CH3 free radical attacks your chlorine free radical, and it forms a bond finally you will get your CH3Cl, and that was what you required. This is your methyl chloride, this is your alkyl halide. Finally your alkyl halide will form, but there is a catch to it. You will also get a chlorine free radical which will form after that. So this chlorine free radical, it has a lot of options. This is also electron thirsty. Now since it is electron thirsty, it can attack this, it can attack your CH4 which was present in the solution. It could go attack your chlorine molecule and form Cl2. It has a number of things. So there will be a mixture, or there will be a continuous reaction that will be forming or occurring. So now since we already got our product, we need to terminate this reaction, so that is our next step. We need to stop this reaction from going more further since we already got our product. So this is our last step, that is termination. How do you terminate this reaction? How will this reaction actually terminate? So this reaction can terminate if your chlorine free radical goes and attacks another chlorine free radical which would have been present in the solution. It's a solution, it's a place where multiple reactions are occurring. So your chlorine free radical might go and attack this chlorine free radical in that, and let's say this reaction was occurring in this beaker, and so you have a lot of reactions which are occurring, and so this chlorine free radical will find another chlorine free radical and attack this and attach and form a chlorine bond, or Cl2, and this reaction stops here. Or this chlorine free radical will go and attach your CH3 free radical and it will form CH3Cl. That could also happen. Yes, it could form CH3Cl, and this was also a required product. And another possibility, you could also have your CH3 free radicals go and attach to another CH3 free radical, forming ethane. So that is a major possibility in this, and this ethane formed will be in traces. Now this is an important question right here. This is a really important question when it comes to your class 12 boards or your midterms or your finals. They could ask about ethane. Is ethane formed during chlorination or during the formation of haloalkanes? Yes, it is formed in very small amount or in traces during the termination of our chain. That is a possibility. Similarly, for bromination, if you talk about bromination, then it is the same concept that is applied here as well. You generally talk about your basic stuff, that is your substitution by bromination, and in this case the basic difference is that your halogen atom changes and it is bromine in the place of chlorine. So I'll consider an example: CH3, CH2, CH3, and you are going to put sunlight or heat it in the presence of bromine, and then you will get your CH3, CH2. Now here also two products are possible. Your bromine atom can go and attach to this particular carbon atom. This is your primary carbon atom, or it could also go and attach to your secondary carbon atom. So that is your secondary carbon atom. Now always remember, I always told you that secondary free radical is always more stable than primary free radical. So this product will be your major product that will be forming. I'm not saying that this product won't form. Of course this product can be formed, but this is your major product which will be forming because it is more stable and more percent of compound is present, and this is your minor product that will be forming because it is less stable and it will be less, the percentage will be less. Moving on, now iodination. Now iodination is an important topic here, and some of the key important concepts lie in this iodination as well. Now when it comes to iodination, you will have a reversible reaction. Let me give you an example. Let's say this is my methane. Methane is the best thing to, you know, to understand stuff. Methane always helps to understand complex concepts. Just use this simple alkane here, methane. Okay, CH4 will, you know, attack iodine. Okay, CH4 and iodine, this reaction, and what will I get? I'll get CH3 iodide plus hydrogen iodide, and this is a reversible reaction. This is a reversible reaction. Okay, now this is a reversible reaction, so this product will keep on turning back into reactant, and reactant will keep turning into product, and this process will keep occurring. So product yield will be less, so we won't be able to yield much product, and we need to stop this. We do not need this iodination as a reversible reaction. What do? So this is a reversible reaction, and to make it irreversible, or to gain more haloalkanes, we need to make it proceed in forward direction instead of, you know, making it proceed in the reverse direction as well. So we need to stop this irreversible property of this reaction. How do we stop this irreversible property of this reaction? The answer is simple. We use our nitric acid or hydrogen iodide or nitric acid. These are your two things, your oxidizing agent which can be used. These are your oxidizing agents. So these can be used to stop this reversible reaction. Now this is a very important question when it comes to your midterms or your, you know, unit tests or finals. For that matter, this is an important question. To make an iodination reaction irreversible, we need to use these compounds. So what happens? What is the function of these compounds? What do they do actually? Well, if you look here, something that this hydrogen iodide is formed. Now if I remove this iodine will not go again and react to this particular methyl iodide. We need to stop this from reacting with methyl iodide so that further iodination does not occur. So I need to remove this. I need to do this. I need to remove this. So how do we remove that? So if I remove hydrogen iodide, I need to react it with our HiO3 or nitric acid, and what will happen is that this particular iodine will react with this particular iodine, and I will get my molecule here, and then I will also get my water molecule as this will react with this. So I'll get H2O molecule here, and this will stop the reaction. This is happening since it is converted into I2 iodine, and so this hydrogen iodide does not have anything to react with. So this will not react with our CH3I, and thereby it stops our reaction. It puts it to a halt, and there will be no further reaction after this. So this reaction is from irreversible, it has been converted to a reversible reaction. Now this was an important concept in this preparation of haloalkanes, using our alkanes by halogenation of alkanes. So we studied a lot of topics today, but we tried to simplify these topics into an easy way of understanding. So we studied our fluorination, we studied chlorination, we studied bromination, we studied iodination. Out of this, I have also told you the mechanism of how these reactions occur and what is behind the scene, what is actually happening behind the reaction, and mechanisms are something which actually improve our concepts. Okay guys, that was about the halogenation of alkanes and preparing haloalkanes using the halogenation of alkanes. In the next video, we will talk about halogenation of alkenes and how we can use this particular method to make our haloalkanes. Thank you for watching. Have a nice day ahead.